Let's go learn some properties of these integrals. This is going to be basically just the rules, the shit you're allowed to do. Imagine trying to find limits if you don't know any limit laws. Imagine trying to find derivatives, but you don't know how any of the derivatives work. We can't do anything unless we understand this part. And if you actually take a second to understand this piece, it's going to help you to get everything else later, or you can continue to struggle throughout this all the way through Calc 2. Getting a good foundation of just the properties is going to help out a ton. I think they're actually really freaking straightforward. And you might already know them, so what the hell do I know? Let's just get into it. The properties of the definite integral. So I got a few of them here. Let's jump into this first little two right here. We'll look at the others in a second. So we're saying, let's look at this. We'll call this one first. Let's go. And it says that if we take an integral of f of x, both of them have f of x dx. It's the same shit in both of them. But what it's saying is if you change the bounds, say we're going from b to a, or maybe like 4 to 5, we can say that, well, we can just turn them around as long as you change the sign. So let me give you an example. Let me give you an example of this. This would be, say, maybe from 1 to 3 of f of x. Oh, no, let's not write f of x. Let's give you an example of x squared dx. Well, we could say that this is the same thing as the negative of, just flip your bounds. Just turn those little bounds around. Put the 1 up top, put the 3 down below, times x squared dx. And this is going to come from the idea that the change in x is equal to b minus a over n. But if you were to turn that around and go from b to a, like this example, like that one there, well, shoot, then our change in x would actually be a minus b over n. And if you factor out the negative, you find out it's absolutely just the opposite of what we just found. And that's why the sign changes. Now for you, as a student, I know I don't really have too many math majors come through my doors, or virtual doors now, but a lot of physics and stuff, you just gotta know this frickin' rule. Get it locked into your brain, tattoo it on you, do something, because it's useful. You don't have to use it. You can do extra steps if you feel like it. But this is one of those that can kind of shortcut things, especially once you get to 5.4, or when you want to do applications of physics. That is huge to flip your bounds. So take it or leave it. Flip your bounds, change the sign. Now for this next one, right down here. This is a mellow one. This one's pretty clear. So we're saying going from point A to point A. Oops. Well, x goes from A to A. We want to find the area underneath the curve. All right. Here's your x. Here's your y. Let's say we got some sort of curve. Yeah, there it is. There's our curve. Y equals f of x. We're stoked. And now we want to go find the area underneath this curve. We're like, okay, let's go get the area. From point A to point A. We're like, go get that area. There's no area. There's no frickin' base. Now, I might draw my line and it might look like it's thick and there's something there. No. Lines have no length. There's no measure to them. We draw them with measure so we can see them. But in actuality, there's no line there, there's no thickness, there's no base, hence there's no area. So your example, if you were to go from 2 to 2 of x cubed dx, you just say you didn't go anywhere, there's no freaking area. Zero. Nothing. Let's go to our next ones. All useful. These are all freaking, well, that one there is like, I don't know how often you'll actually use that. But here we go, we got a few more. So let's look at number 1. Oh, before you get to number 1, 2 and 4 are the same thing. I'm gonna write them in with both the same thing. So, but let's look at number 1 first. And I know this to be true, but this isn't one that's typically on my brain as I'm solving things. So let's draw out the idea. Our x's and y's. Now, what we have here is our function that's inside is just a constant. It's just a number like 4, 6. But that's your y value or your f of x value. So let's maybe draw it in. We're like, well, it's just y equals some sort of constant. The way I drew it, it was positive, but it doesn't have to be positive. It could have been negative, right? It's just the height. And if we're going from some point A to some point B, dude, we're finding the area of a rectangle with its height being c and its width being b minus a. Hence, it's c times b minus a. If it was ever a constant, it's just the length of the interval times the constant. For example, 1 to 4 of 5 dx would be equal to, let me change my color. What's the difference between 1 and 4? So that'd be 5 times 4 minus 1, so that's 5 times 3, which is equal to 15. Right? Because it's from 1 to 4 is 3. 3 times 5 is 15. That's it. Constant rule. Now for 2 and 4. This is the shit that you wanted in derivatives. Could you break it up term by term? When you did antiderivatives, didn't you break it up term by term? Didn't you go through? If you were to have, say I gave you the f of x is equal to 4x cubed plus x squared minus 1, wouldn't you go this term, then this term when taking a derivative? Or finding an antiderivative? Well, the same shit's true for our integration as well. Saying that if you were going from, I don't know, 1 to 2 of x squared plus x minus 3. So now I'm doing this one and this one all in the same shot. All in the same shot. Plus or minuses. Look at that. There's a plus and there's a minus. There's not much to it. It's 1 to 2 of x squared, and then we write the dx. That dx, you got to get used to writing it. Alex mentioned it to us in our class that she forgets it. I do too. We all do, but that's the notation saying the integral's done. It's called the differential of x, but for our case, it's just d whatever the frickin' variable is. Since we're using x as we write dx, it's telling you with respect to which variable. There it is. Broke that shit up into 3 pieces. So you can go through and just do it term by term. That makes life easy. Doesn't matter whether it's a plus or a minus. And now for number 3. And this one's mellow as well. You already know this freaking rule. This is true for derivatives, and it's true for limits, and it's true for factoring, and it's true for everything. If you just have a constant, you could yank it out to the front. Give you one quick example, and we're going to finish this one up. Saying if you're going to go from 7 to 12 of 5 times, I'm going to call it t squared this time, dt. Well, we can just yank this 5 on out to the front. Sorry I changed up the variables on you, but I just want you to know it doesn't have to be x. Just give it whatever the hell you want. And there we go. Just saying you can rip the constant out to the front or the coefficient out to the front and just deal with it. It can remove noise for you. So there it is. There's our rules. On our next one, I'm actually going to teach you some of the games. They're right here. We'll play this game here. We'll mess around with these where I give you 3 pieces of information and then we go find 6 of them. So you can see all the properties in action. I'll see you in the next one.